There's been a large gap in time between the last video on the subject of gravity. I was looking at the most recent one I did. I think it was in March of a year ago now, 2014. Since then I've been doing videos on other things such as the effect of strong winds on the safety of an aircraft in flight, particularly when turning. I've gone back to writing now more about physics, and I just finished, I think it's the 6th article on that, or essay on that, on the subject of energy, and that's ready to be published today or tomorrow. But I wanted to finish off. I was looking at the 9th video I did in March of 2014 on the subject of energy equations. And I did one after that on the orbit of the moon. But I didn't really finish up with gravity. I'm going to be talking about it more, or rather writing about it more than talking about it. I thought I'd make this more of a sales pitch, perhaps leave some of the technology out of it, and try to persuade. Let me just put my light on. Try to persuade scientists to reconsider what causes gravity, because I think that we have been for a long time looking in the wrong places. Now about 100 years since Einstein's general theory of relativity, and it's 350 years or so since Newton's theory, and there are flaws with these. There's still, not we, the scientists and mathematicians are still looking at the general theory of relativity to find out whether it needs a cosmological constant, for example. And Newton's equations are perfectly good for what he could experiment with at the time, which was on the Earth's surface, and by observing heavenly bodies in their orbits, which are mostly circular, close to being circles. And his theory works fine with a circular orbit, but not, I think, with a vertical drop. It's very difficult to produce experiments to test the gravity on a vertical drop. You'd have to go far enough up in order for the inverse square law or whatever other law affects the gravity, but according to the distance. I think it's the reverse, that the square, that gravity is proportional to the square of the distance. But you'd have to go up 1,000 miles to get a decent effect from that. And to send something straight up 1,000 miles and then let it fall in free fall and measure its acceleration in that state, measuring gravity, is not easy to do. You can't, for example, put an accelerometer into it, because accelerometers cannot measure the acceleration of a body in free fall. Accelerometers measure the force on a body from another source, such as a thruster or push. So it's very difficult to experiment, and it could well be that there are vast differences in the way that gravity works when you're well away from the Earth and you're not in some circular orbit. A circular orbit is very simple, because in a circular orbit the energy is constant, the potential energy is constant, the kinetic energy is constant, although I think that it's unstable and the body would not stay in circular orbit, but that's for another time and for another discussion. But I think that we know a lot about circular orbits, and we know about gravity on the Earth's surface, where no one questions that the force acceleration due to gravity is approximately 32 feet per second. But when you get into further out, it could be different. What I want to do, as I said, is to get more away from the technology, from the science of it, and talk about some practical matters. For example, I understand we're still looking for particles such as gravitons, or for gravity waves, and we've not found any, not found one. And yet, if you watch carefully, this, not only, even before I'd released it, had detected every graviton that it encountered. It not only detected it, it identified it as a graviton. It assessed the intensity of the field, and it responded instantaneously. If this can do it, why can't we do it in a way that shows that it is a graviton? I've had quite a lot of experience at measuring particles. For 13 years I worked at Harwell. One of my jobs was to measure the energy of neutrons. Neutrons are very, very small particles, although they are large as far as, and very dense as far as nuclear technology is concerned, but they're very small as far as we're concerned. And I did a little calculation just now as to supposing there are particles called gravitons that somehow can pull instead of push. I don't know how they do that. But if the Earth were emitting particles, would these particles be able to move something? And it's very interesting that I can push something, say at 5 miles an hour at my age, with maybe even as much as 100 pounds of force. How can a proton or something invisibly small produce a measurable force? Well, particles travel, and photons, for example, travel at the speed of light. Neutrons are a little slower, but they still travel very fast. Photons travel at the speed of light, which is 186,000 miles a second, and I would be pushing it, say 7 or 8 feet per second, and about, say, 4 miles an hour. If you consider the ratio of the speed of light to the speed at which we move and the speed at which our motors move, you find this enormous. 186,000 miles a second is 3.6 or 3,600, 3.6 times 1,000 times faster when you consider it to be in miles per hour. It travels a greater distance by 3.6 thousand miles. And then when you square that to get the kinetic energy, you find that the energy of something traveling at the speed of light is something like 10 to the 10th, that is to say, sorry, 10 to the 15th, and that is to say about a number like 2 with, say, 15 zeros after it, more energy than I can push. So it's very believable that a small invisible particle can move something if it's traveling fast enough. So it's not out of the question that it could be particles. It's just that we just haven't found any. This could find one, but I worked with all kinds of detectors 50 years ago, what I call proportional counters, which were boron trifluoride filled like a Geiger counter, and then scintillation counters, ion chambers, photographic film, all kinds of things that could detect particles. And now, of course, we have accelerators and cloud and bubble chambers that can detect particles. They should have no problem in detecting something that this can detect. And so I think it's about time we just stopped looking for particles. And waves are the same thing, because waves and particles exist side by side. We know that with light. And so that's not the cause of gravity. And so if you take then Einstein's theory, was not that it was particles, not even that it was a force, but it was that the space between bodies of mass is filled with an energy field. But he did not explain as to how that energy field gets out of the Earth and into the atmosphere, or rather, it's not atmosphere, but into space, into empty space, even to a vacuum, and to form the energy field. And I firmly believe that the cause of gravity is the conservation of energy and momentum. And this to me is very believable. I believe that if you have, say, the sun and the earth, like that, with 92 million to 93 million miles away, cannot exert any force on the earth. There's no way that it can do that. But The energy between them, this space, is something that exists. Although there is a vacuum, it still physically exists. And because of that, if it cannot change, then it stays the same. And so, if this space stays the same, and this body in movement, there's nothing to make it move, there's also nothing to make it stop. We know that all of these bodies received movement at the Big Bang, and they've kept some of that movement. And so this movement remains from the Big Bang, orbiting the Earth at about orbiting the Sun at about 67,000 miles an hour. That can remain constant. Constant kinetic energy, constant potential energy, that conserves energy. And it can stay that way. And I think this is a stable state. That this is actually an equilibrium state where the energy is equally divided between the two bodies, and that all heavenly bodies end up in a circular orbit because it's a stable state, and there's no need to have any forces at all. But when you have a vertical drop, it's a different matter. And if you were to drop something from the sun, or let's drop it from the moon to the Earth rather than from the Earth to the sun, and not drop it in fact from the moon, but to drop it from the other side of the Earth, so the moon doesn't interfere with its gravity. Drop it from the distance that the moon is from the Earth. Drop it vertically. But you need not go that far, 127,000 miles. You could drop it from 1,000 miles. If you could do that, you could show that the force of gravity is caused by the conservation of energy momentum, because you would not get the inverse square law, as Newton and Einstein, I think, agreed with. You would get, in my opinion, you would get the greatest acceleration at the greatest distance, because it would follow a cosine curve with time, due to keep the kinetic energy plus the potential energy as constant. So that's my sales pitch for a different theory, and I think it's time that we began to look at something quite different. I think we're barking up the wrong tree. Thank you.